Alright, so we're going to be looking a little bit at how to do a data description. If you notice here in the rubric, the data description is 10 points, so you want to take your time and make sure you're actually looking at the rubric and making sure you're having all the pieces here for the data description. The data description, the objective here is to accurately describe the data that you record. So you're looking at observations, were objectively described in paragraph form and/or data reported in words immediately following the data tables. Now, the objective here sounds like it wants you to give a verbal data table, but I'm going to warn you, please do not do that. That's what data tables are for. So what you're going to be trying to do here is trying to point out things the reader should notice about your data. Like, are there any trends in that data? Meaning, does the accelerations or the velocities, do they go up? Do they go down? Do they go up by a even amount? Do they go up by a differing amount? That's an important thing to kind of figure out. So as we start looking across the table here, number 10, 10 points out of 10, all data is fully and accurately reported. All observations and trends of data are objectively described in paragraph form while highlighting important data. As you kind of go right, things get a little worse. So here it changes from all data to most, and then most, that's the only big change between 10 and 8. 6 points, some data is fully and accurately reported. So what I'm really looking for as I grade these things is that you're getting all the trends that show up in your data table. I will look for them myself and then go to your data description to see if I see you describing them. If you look at the template here, I'm going to write an example here as well, but you want to make sure that that's the objectives again. Your data description itself should be about a 4 to 5 sentence paragraph. This shouldn't be a verbal data table. We don't want to do that. Try to identify your independent variables and dependent variable in your first paragraph or your first sentence, and then begin describing the relationship between these two variables. Once again, does the dependent variable go up or down as the independent variable increases? Does the dependent variable change by a constant, or does it change, or does the change vary? And that's an important thing to kind of look at. So in this other document over here, I have a prepared data section. And let's write a data description. Now remember, your calculation section will come next. So your calculation should be in between your data description and also your data tables. So looking at this particular section here, I want to start out with my independent and dependent variable. So in this particular lab, the independent variable was the added mass on the cart, while the dependent variable was the acceleration. The accelerations in this lab were both measured as well as predicted using Newton's second law. Now, the data I have here is purely made up, so looking at some of this stuff, it's not exactly going to look like your data. But looking at our calculated accelerations, if you look here, it seems like we're going up, getting faster as more mass is added. But here we have this one random data point here, which looks like it's going to be what we're going to call an outlier. We'll come back to that in a little bit. And if you look at the differences between these trials, between here and here, this is a difference of 0.4. Okay, between these two data points, we have a difference of 0.14. And then between these two data points, we have a difference of almost 0.2. So even when we are going up, it seems like we're going up by more and more and more as this acceleration begins to, as it continues to rise. So in this situation here, I might say, as the mass of the cart is increased by 0.1 kilograms or 100 grams, the calculated acceleration, or I can probably actually change this to the experimental, since that would make a bit more sense overall. Acceleration increased by uneven amounts. Between trials, the experimental acceleration. And here I'm going to do a little bit of math just to kind of show that, the same kind of thing I did before. The experimental acceleration changed by, and once again the difference between these two was 0.04. And I don't see that thing, so we'll just say that. That's fine. Trials 1 and 2. And then between these two trials here, we increase by about 0.14 meters per second squared between trial 2 and 3. And between trial 3 and 4, we went up by roughly 0.2. And 4. So this gives a pretty good accurate description here that we are actually increasing by more and more and more as we put more mass on it. Lastly, I might say that the acceleration in trial 5, and I'll be more specific here, experimental acceleration in trial 5 was an outlier, meaning that it was too far away from the other measurements for us to actually really want to count that in our description. And I might do something similar with the predicted accelerations too. We don't have to identify the variables anymore, but we can say for the predicted accelerations. And here we see this is different. It's dropping. The accelerations drop as the mass is increased. Once again, let's look between the trials here. Between trial 1 and 2, the acceleration changed by, and this time it looks like it dropped by, we can actually change this, it dropped 0.14. Then in between trial 2 and 3, we dropped by 0.1. Between these two trials, we dropped by roughly 0.7 if I round a bit. Sorry, 0.07. And finally, dropped by 0.06. between trial 4 and 5. There are no outliers in this data set. You can even talk a little bit about the percent error too. Now, these percent errors are quite ridiculous, but you can always just keep in mind that a good percent error is at around 5 to 10%. If you get it below 5%, that's excellent. So in this case, I would say the percent errors in this lab were mostly, let's change that. In this lab showed that most of the experimental and predicted accelerations were very different. The only trial which showed a close percent error was trial 4, since it was below 10%. Where we can say the second best trial was trial 3 with a percent error of 53%. Meanwhile, the other had errors greater than 100%. And this right here is a very good 10-point data description. If you notice here, it only took us about 12 minutes to write this. So if you just look at your numbers and compare them to your masses, it should not be too difficult to kind of figure out how to write a nice data description. Once again, if you have any questions about this, please feel free to ask. Good luck.